This is the first video about oxidation of alcohols. As you can see from the objectives, what we're looking at over the coming videos is to be able to write equations for the oxidation of alcohols. Firstly, with atmospheric oxygen, and then secondly, and perhaps most importantly, with acidified potassium dichromate. This is a mild oxidizing agent. It's more interesting because it results in the formation of more interesting organic molecules called aldehydes, carboxylic acids and ketones. What we need to understand is how changing the reaction conditions will result in the formation of different products when beginning with primary alcohols. We also need to know what's formed when a secondary alcohol reacts. And finally, we need to know why a tertiary alcohol is resistant to oxidation when using acidified potassium dichromate. So, to begin with, alcohols reacting with oxygen. What I'm going to ask you to do is to balance the following equation. Pause the video, have a go yourself. Okay, hopefully you're clear that when we react this alcohol with oxygen, we're going to make some carbon dioxide and water. If you weren't sure about that, pause the video again and have another go at balancing the equation. We can see that there are 4 carbons in butanol, so we're clearly going to make 4 carbon dioxide molecules. There are 10 hydrogens, so we're going to make 5 water molecules, and altogether that gives us 13 oxygen atoms in the product, so we need 13 oxygen atoms in the reactants. Don't forget this one. That means there needs to be 6 oxygen molecules. Now for something a little bit more interesting. Let's move on to the work to do with acidified potassium dichromate. As you can see, acidified potassium dichromate, K2Cr2O7, it looks quite a complex compound. And for this reason, we use this symbol, an O in square brackets, when we're writing equations that involve acidified potassium dichromate. It just makes it easier to balance the equations, and it's what we expect to see at A level. Now there are 2 possibilities when we take a primary alcohol and oxidizing it using the acidified potassium dichromate. So, first of all, taking butanol, we can see that the functional group changes. This is called an aldehyde, so this is the aldehyde functional group. The oxygen atom has removed a hydrogen from the oxygen and a hydrogen from the adjacent carbon atom to make water, leaving behind this aldehyde functional group. The rest of the molecule remains unchanged, and the equation balances. There's an alternative possibility. This time, the functional group that we form is this one. Slightly different, but with some similarities to the aldehyde. This functional group is called a carboxylic acid. Again, some water is made, and again, the rest of the molecule remains unchanged. But this time, the equation does not balance. There's an extra oxygen atom in the carboxylic acid compared to the aldehyde. So this time we need to use 2 oxidizing agents. The hydrogen attached to the oxygen and the hydrogen off the adjacent carbon atom have been removed to form the water. In terms of naming these substances, this aldehyde is called but, 4 carbons, and all the carbon-carbon bonds are single bonds, al, for aldehyde. There's no number here because the aldehyde group is always on carbon number 1. This is called but, and oic acid. Again, this is on carbon number 1, so we don't need a number. Primary alcohols can be oxidized to form aldehydes, or primary alcohols can be oxidized with extra oxidizing agents to form carboxylic acids. How do we decide which one happens? Well, that depends on the reaction conditions. The first one is if we do a process called distillation. And the second one is if we do a process called reflux. And we'll look more at these two processes in a later video. What do you see when these reactions are happening? Potassium dichromate contains the chromium in a +6 oxidation state. And during the reaction, the oxidation state of the chromium changes to +3. And as this happens, we get a colour change. The chromium oxidation state changes from +6, which is orange, to +3, which is green. So when you oxidize a primary alcohol, you can see a colour change. But it's not the alcohol, or the aldehyde, or the carboxylic acid which are doing this, it's the chromium, orange to green. That's really important. It's really, really likely to come up on your A-level exam. Let's have a look at what happens with secondary alcohols. With a secondary alcohol, we get a similar outcome. The oxygen, in terms of the oxidizing agent, removes a hydrogen from the oxygen and a hydrogen from the adjacent carbon atom. And so we end up with this functional group, a C double bond O sandwiched between two carbon atoms. This is a ketone. It's similar to an aldehyde in terms of the carbon-oxygen double bond, but there's no hydrogen here. We've got the extra carbon atom. We still make water because the oxygen, the oxidizing agent, removes the hydrogen and the hydrogen from the central part of the molecule. The rest of the molecule is unchanged. When we name this prop, because it's 3 carbons, and because all the carbon-carbon bonds are single bonds, one for a ketone, propanone. We can't do any further oxidation with this, so the reaction conditions are less of an issue here. And generally, what we would do would be a reflux. There's only one possibility. Tertiary alcohols. This is much more straightforward. We can see a hydrogen on the oxygen, but the adjacent carbon atom has no hydrogens. So, in terms of oxidizing, with acidified potassium dichromate, nothing happens.